Assalamu alaikum dear students. Okay, last time we were discussing a group of order PQ and we have shown that a group of order PQ is cyclic when P and Q are distinct primes, P is greater than Q and also P is incongruent to 1 mod Q. So that was order of G is PQ and P is greater than Q with P is incongruent to 1 mod Q where P and Q are distinct primes, then G is cyclic. Okay, last time we have proved this theorem. If G is a group of order PQ where P and Q are distinct primes, P is greater than Q and P is incongruent to 1 mod Q, that is, this means that Q does not divide P minus 1, then G must be cyclic. Okay, so using this theorem, we have seen that if order of G is equal to 15, so here this is 3 and 5, you take P is equal to 5, Q is equal to 3, here P is greater than Q and P is incongruent to 1 mod Q since 3 does not divide 5 minus 1. Since 3 does not divide 5 minus 1, so you can write P is incongruent 1 mod Q. That's why a group of order 15 with respect to this theorem is cyclic. Okay. Now today I am going to prove that we can prove directly that a group of order 15 is cyclic without using this theorem, and in fact I want to give an idea to prove some particular groups directly by means of Sylow's theorem. Okay, so we can prove this. Let order of G is equal to 15, that is 3 into 5. Then by Sylow's first theorem, what is the Sylow's first theorem? Sylow's first theorem states that if a prime P divides the order of a group G, then G has at least one Sylow P subgroup of order, whatever it is. So in this case, 3 is a divisor of 15. So a group of order 15 has a Sylow 3 subgroup of order 3, and similarly it has a Sylow 5 subgroup of order 5, right? So by Sylow's first theorem, G has a Sylow 5 subgroup of order 5 and a Sylow 3 subgroup of order 3, right? Since 3 and 5 are the divisors of 15, so using Sylow's first theorem, it is clear that G has a Sylow 3 subgroup and a Sylow 5 subgroup, right? And further, the order of Sylow 5 subgroup is 5 and a Sylow 3 subgroup is 3 because 3 and 5 are the factors of 15. Okay, so let h is equal to x, so that x power 5 is equal to e, and k is equal to y, so that y square is equal to e, y cube is equal to e. Okay, look at this. I have taken H as the Sylow 3 Sylow 5 subgroup, and K is the Sylow 3 sub. So since a group of order 5 is cyclic, 5 is a prime number. Similarly, 3 is a prime number, and you know that every group of order prime number is cyclic. So that's why I'm taking these two groups as cyclic, right? So let H is a Sylow 5 subgroup and K is a Sylow 3 subgroup. So look at these two groups. This means that here in H we have 4 elements of order 5, and here in K we have 2 elements of order 3, because these are the cyclic groups of prime orders. And you know that all powers are prime to 5, means 5 is a prime number. That's why x power 1, x2, x3, x4, all powers 1 to 4 are prime to 5. And we know that if G is a cyclic group of order n, then for any number k which is lesser than n, a power k also generates G if and only if k and n are relatively prime. That's why if k and n are relatively prime, then ak is the generator, in fact, right? So we have a theorem, k and n are relatively prime if and only if ak sided ak power n is equal to e for a g is equal to a sided a power n is equal to e. So this is a very well-known theorem to find the number of generators of cyclic group. If G is a cyclic group of order n, then any power a power k also generate G. A power k power n is equal to E means a power k is also a generator of G. This is also G. This is also G. If and only if k and n are relatively prime. So whenever you want to know that how many generators you can have in a cyclic group of order n, you need to count the number of powers of the generator which are prime to n, right, with respect to this theorem. So since 5 is a prime number, so all powers 1, 2, 3, 4 are relative prime, so all are the generators. So other than identity, all elements of this group are in fact the generators. Similarly, other than identity, all elements of this group are the generators. So this means there are 4 elements of order 5 and there are 2 elements of order 3. Okay. This shows that thus we have 2 elements of order 3, namely x and x square, and we have these are y and y square, this was square, and we have 4 elements of order 5, namely these are y y square. So these are x, x square, x cube, x4, because you have assumed that h is equal to x such that x power 5 is equal to e, and k is equal to y such that y square is equal to e. Okay. Y cube. So y and y square are the only elements of order 3, and x, x square, x cube, x4 are the elements of order 5. Now, if A is any element of order G, then by Lagrange theorem, the order of A also divides the order of G. But G is equal to 15. So that order of A is either 1 or 3 or 5 or 15. But you already have counted the elements of order 3 and order 5. So that particular element is in fact an element of order 15, right? So if let x, so you take A, let A belong to G, then by Lagrange theorem, order of A divides order of G, which is equal to 15. Hence, order of A could be equal to 1 or 3 or 5 or 15. So, can you find out how many elements, such elements there exist in G, and also what is the possible order of A? You know, you already have counted the elements of order 3 and the elements of order 5 and the identity element. So, the order of this element must be 15, right? Since there exist (15 minus 1 plus 3 plus 4) elements of order 5, order 15. You know, this one is stand for the identity element, and 2, there are 2 elements of order. There are 2 elements of order 3, and there are 4 elements of order 5. So 4 plus 2, 6, 7. This is equal to 8. Since there exist 8 elements of order 15, because these are the elements order of 1, order of identity. This is the 2 elements of order 3 and 5 elements of order 4. So the rest of the element must be of order 15, right? As we already have counted elements of order 1, 3 and 5. Consequently, order of A is equal to 15. And also you can verify that there exist such 8 elements. You know, if you find, order of the generator is in fact the order of the cyclic group. Since order of A is equal to 15, so A must be the generator. And the corresponding group G is in fact the cyclic group, right? And you can verify, if you take phi of 15, phi of 15 is the number of those elements which are prime to 15. Okay, so this can be calculated phi of 3 and phi of 5 and you know phi of 3 is 2, phi of 5 is 4, this is equal to 8. Also, we know that there are 8 numbers which are prime to 15, means say you can count the numbers from 1 to 14 which are prime to 15, right? So this means that 8 powers of A are in fact the generators, right? So that's why there must exist an element A of order 15. This means that A generates G. That is, G is equal to A, such that A15 is equal to E, so which is isomorphic to C15. Hence G is cyclic. Okay. So you have shown without using that theorem directly that a group of order 15 is cyclic, right? And you know that every cyclic is abelian, so there does not exist any non-abelian group of order 15. So directly you can show, because you know that there is a Sylow subgroup of order 3 and there is a Sylow subgroup of order 5, and a group of order 3 of course is cyclic, so because it has two elements of order 3, and similarly a group of order 5 has 4 elements of order 5. So they are in fact 2 plus 4 plus 1 is the identity element. There are 7 elements which could have order 1, 3 or 5. And since the order of element is in fact the order of the divisor, which was the divisor of the order of the group, which was 15. So the divisors of 15 are 1, 3, 5 and 15. So the rest of the elements, the order of the rest of the elements is in fact 15. This means that there are 8 such elements if you count, because you have counted 7 elements and the rest of the elements are 8. So you have 8 elements of order 15. Mean to say that you have a generator. You have such elements which can generate the entire G. That's why G is cyclic. Okay. Similarly, by using Sylow's theory, I can find groups of order 6. Similarly, I can establish that up to isomorphism, there exist exactly 2 groups of order 6. One is C6 and the other is S3, which is isomorphic to D3, right? So I can show with the help of Sylow's theory that these are the 2 possible groups. So if order of G is equal to 6, which is equal to 2 into 3, this means that you can take H is equal to X, such that X cube is equal to E, and then K, which is equal to Y, such that Y square is equal to E. So these are the 2 Sylow subgroups of order 3 and a Sylow subgroup of order 2. And you know that index of H in G is 2, that is 2. So here note that index of H in G is equal to order of G by order of H, which is equal to 6 by 3, which is equal to 2. So this implies H is normal in G. H is normal in G, right? Look at here. You can find index, since index is 2, so this H is normal. So Sylow 3 subgroup is normal in G, so is unique as well. On the other hand, you can also find that by using Sylow's third theorem, K is the number of Sylow 3 subgroup, which is congruent to 1 modulo 3, and U, that is 1 plus 3t, and you will see that t is equal to 0 will survive only. So K is equal to 1. So there exists exactly 1 Sylow 3 subgroup, which must be normal, being unique. Okay. So then yx y inverse belong to H. Look at yx y inverse belong to H. For y belong to K, which is subset of G, that is y belong to G. Since H is normal, in G, so you take an element y belong to G, then by the normality, yx y inverse is in H. Okay, so using the normality, but you know that H is a cyclic group, and it has only three elements. One is E and the X and the X square. So this yx y inverse is in fact either E or X square. But H is equal to Ex x square, hence this yx y inverse is equal to E or X square. So these are the possibilities. Now I will discuss separately. The first one would not be possible. So there are the two possibilities that would give you two groups. Okay. So how can you prove this? Now, okay. So if yx y inverse is equal to E, this implies x is equal to y inverse y, right, which is equal to E. So this implies x is equal to E, a contradiction, because x is the generator, so this is not E in fact, right? So so this case is not possible, hence yx y inverse is not equal to E. Now second one, if yx y inverse is equal to this one is x, if yx y inverse is equal to x, this implies yx is equal to xy, means that this is abelian, right? But then this implies yx power 6, in fact y6 x6. And you know this thing is, if xy is equal to yx, then you have a result. If xy is equal to yx, then yx power n would be equal to yn xn. This is possible because you write this yx n times and then swap x and y, right? You can keep all y's on the left side and all x on the right side. So that's why if you're using this continuously again and again, successively, then yx power n can be written as y power n, x power n. So that's why yx power 6 is equal to y6 x's, and this is equal to in fact y square 3 and x cube 2, that is E, which is E. And also I can show that there is no power before this which leaves identity. So that's why yx in fact exhausts all the 6 elements of your group of order 6. That's why it is cyclic, right? So you see yx power 1 is equal to yx power 2, this is y square x square, this is equal to in fact x square, and yx3, this is y cube x cube, this is equal to y, right? And yx power 4, this is y4 x4, this is E, and x, this is x. And yx power 5, this is y5 x5, y5 is y and x5 is x square. So look at the elements. These are the 6 elements. One is yx, second is, you count here, E, x square, x. These are the 3 elements. Then yx, then yx square. So these are the 6 elements. but all are generating by yx. This means that in this case, G is equal to yx divided by x power 6 is equal to E. This means that G is a cyclic group of order 6. Okay, thus in this case, G is equal to yx sided yx power 6 is equal to E, hence G is isomorphic to C6, right? So if you take yx y inverse is equal to x, then you will get yx is equal to xy, that is abelian, and from here you can exhaust all the elements by taking different powers of yx. So means to say that yx power 6 is equal to identity, means to say that yx is in fact a generator of this group. So it's a cyclic group, and you know that the cyclic group of order 6 is C6. Okay, and then if you take next case, if yx y inverse is equal to x square, and you know this is equal to x inverse, since x inverse x cube is equal to E, so this imply x square is equal to E, this imply x square is equal to x inverse. So x square is equal to x inverse, so this imply yx is equal to x inverse y, hence the group is you have y x sided, or you can write xy sided x cube is equal to y square is equal to E, with yx is equal to x inverse y. And you know what is this? Using the condition, you can also show that xy is of order 2. Okay, so what is this? This is in fact this G is this, so this is in fact S3, which is isomorphic to D3. Some people like to write D3. Okay, we have shown that there are up to isomorphism, there are two subgroups of order 6. One is C6, which is abelian, means to say that there is exactly one abelian subgroup of order 6, and there is exactly one non-abelian group of order 6, which is S3. Okay, so these are the two possible groups. Now I can extend the idea from 6 to 2p. Okay, if you do the same, you can establish groups of order 2p. Okay, we can do this. Instead of writing 2 into 3, why not I write 2 into p, where p is an arc prime. So I can generalize the result. So if order of GP, there you can have theorem, there exists two groups of order 2p, namely C2p and DP. Okay, so if I generalize the idea, instead of 3 I use the p prime number, then I can show that there exists up to isomorphism. Corresponding to every 2p where p is an arc prime, there exists one abelian group, which is C2p, and one non-abelian group, which is DP. Okay, for example, if you have order of G is equal to 10 or 14 or 22 or so on, This means that for particular 10, either you have C10 or you have D5. And for 14, either you have C14 or you have D7. And for 22, either you have C22 or you have D11. So this means that any group of order 2p is either isomorphic to C2p or it is a dihedral group dp, right? So there exist two groups of order 10. One is C10 and the other is D. This means that whenever you have a group of order 10, then that group is either isomorphic to C10 or it is isomorphic to D5. Okay? So whenever you have a group of order 22, suppose you have a group G of order 22 and you have no idea about the elements of G, but this theorem says you that either G is C22 or G is D11. There is no third option for G. This means that there is exactly one abelian group of order 2p, that is C2p, and there is exactly one non-abelian group of order 2p, which is dp. Now let's prove this theorem. Okay, again I will use Sylow's theory to know about these two groups, right? So let's prove this. I want to show by using the same criterion as we have discussed in a group of order 6. Okay. So here order of G is equal to 2p. So again, by using Sylow's first theorem, there is a Sylow 2 subgroup and there is a Sylow P subgroup. And you take H is equal to X, such that X power P is equal to E. And K is equal to Y, such that Y square is equal to E. So these are the two subgroups. This is Sylow P. And you know that again Sylow P would be normal in G. So you can prove this directly from here by finding the index. Also you can use Sylow's third theorem. So first one is, note that H is normal in G as index of H in G is equal to order of G by order of H, which is equal to 2p by P, which is 2. And you know that whenever index is 2, whenever a group is of index 2, then it would be normal in G. Okay? So also you can prove from using Sylow's third theorem. You know that if NP, which is equal to 1 plus say TP, 1 plus PT, this is 1 plus PT, is in fact the divisor of the order of G. And what is order of G? Is equal to 2p. So this is equal to 2p. Thus, NP could be equal to 1. What is NP? NP is the number of Sylow P subgroup in a group of order 2p. And you know from Sylow's third theorem that the number of Sylow P subgroup in a group G is in fact NP, and NP is congruent to 1 modulo P, and also NP is a divisor of the order of 2p, order of that group, which is in fact 2p. So NP, which is equal to 1 plus PT, is a divisor of 2p. So what are the divisor of 2p? NP could be equal to 1, 2, P or 2p. So these two are not possible. If NP is equal to P or 2p, then NP congruent to 0 modulo P, which is against this condition because NP is in fact the congruent to 1 modulo P. So NP is equal to P or 2p is not possible, because NP is congruent to 0 modulo P. If np is equal to p or 2p, right? So these are not possible, because if you take np is equal to p, then p is congruent 0 modulo p, and if you take 2p, then again 2p congruent 0 modulo p. But you need np congruence to, in third theorem, np is congruence to 1 modulo p. So that's why these two cases are not possible, right? Also this is not possible because p is an odd prime, so 1p odd plus something is some integer. So this is integer plus 1, it's an integer must be greater than 2, and a larger number can never divide a smaller number. Also 1 plus pt is greater than 2 since p is odd. So 1 plus pt, which is equal to np, cannot divide 2. Okay, so cannot divide 2, minus 1 cannot divide 2. I can elaborate this like if np is equal to 1 plus pt is equal to 2, say if this is equal to 2, then again I see that there is a contradiction. This implies pt is equal to 2 minus 1. This implies p divide 2 minus 1, which is equal to 1. So this implies p divide 1, a contradiction. A contradiction, as p is odd prime. So in odd prime cannot divide 1. So if you take this 1 plus pt is equal to 2, then pt is equal to 2 minus 1. So this means that p divide 2 minus 1, which is equal to 1, right? So this is not the case, p divide 1. You have a contradiction. That's the only possibility, is that np is equal to 1. This means that there exists a unique subgroup of order p, and we know that whenever the Sylow p is unique, then it must be normal in G. That's why. Or on the other ways, you have directly from here this theorem that whenever you have a subgroup of index 2, then it must be normal. So that's why H is normal in G. Then again, by using the same tactus, this implies Yx, Y inverse belong to H for Y belong to K, which is subset of G, or that is Y belong to G. Look at here. So now again I will use the same logic, since it is an element of a cyclic group, and this cyclic group, the elements of cyclic groups are some powers of x. So this must be equal to some power of the same x, right? Because this is an element of H. So this must be equal to some x power r, okay? So Yx, Y inverse belong to H, since H is normal in G, for taking Y from G and X of course from H, then this element is an element of H, but H is equal to X either X power P is equal to E, hence Yx, Y inverse must be equal to X power R, where for R is less than P. You know, if you take R is equal to P, then X is equal to P is in fact the identity, and if this is the identity, then X is equal to E, which is not the case. In fact, that's why I am taking X power R, R must be lesser than P. Then you know that if this is a cyclic group, then all elements, then E, X, X square, so on, X power P minus 1, all are distinct. These are the distinct elements. So this is one of these. That's why I'm taking X power R, where R is lesser than P, right? Okay, so from here I can write X, say this is number 1, equation number 1. I can label this equation number 1. So X power R is equal to yx y inverse power r, and you know from routine calculation you will be able to know that this r will be shifted here. Like if you take yx y inverse power 2, this is in fact yx y inverse, and these two y would be cancelled, so this is equal to yx square y inverse. So if you take power 2, then this 2 is here in fact. Now if I take power r, this r will be shifted here. So this is equal to yx power r y inverse. Okay. And again, use the definition of x power r. What is the definition of this? X power r is equal to yx y inverse. Then again, I am using the same definition too. Okay, so this is equal to yx y inverse. This is y inverse. This is equal to y square x y square inverse. And you know y square is equal to identity. So this is equal to e x e inverse. This is x, right? So what does it mean? This means that you have established this imply x r into r square is equal to x. This imply x power r square minus 1 is equal to e. So this is the power which is leaving identity. But you know order of x is equal to p. From here, you know, when I am saying that order of x is equal to p, then p is the least positive integer for which x power e is equal to e. X power p is equal to e. Okay. So from this calculation, so this imply x power r square is equal to x. This imply x power r square x power r square is equal to x. This imply x power r square minus 1 is equal to e. But order of x is equal to p, that is p is the least positive integer such that x power p is e. So here p is the least positive integer, and you know that if some other integer is also leaving identity, then this integer must be multiple of p, or p is a divisor of this. Hence, p divide r square minus 1. And what is r square minus 1? You know, this is equal to r minus 1 into r plus 1. So this implies that p divide r minus 1, or p divide r plus 1. Okay. Now these are the two cases, and I shall show that these are the two possible cases. One will generate you the cyclic group C2p, and other will generate the dihedral group of order 2p dp. This is dp, right? So case 1, if you take case 1, if p divide r minus 1, then r minus 1 would be equal to pt, where t belongs to z. So r is equal to 1 plus pt, putting in 1. You know what was the equivalent? That was yx y inverse is equal to x power r, right? And you have established r is equal to 1 plus pt. So we get yx y inverse is equal to x power r would be equal to x power 1 plus pt, which is equal to x into x power pt, which is equal to x into x power p power t, which would be equal to x into e power t, which is equal to x into e, which is x. Right? So what does it mean? So this implies yxy inverse is equal to x. So this implies yx is equal to xy. This means that G is abelian, again by using the property of abelian commutative property. This implies yx power 2p would be equal to y power 2p x power 2p. This is the same step I have explained earlier, right? So whenever yx is equal to xy, you can separate these powers, so you can rearrange, because this is in fact yx 2p times, and by using the commutative property you can swap x and y, x and y, x and y until you will get all y's on the left side and all x on the right side. So this is equal to y square power p into x p square. This is e, which is e. This means that there is an element yx of order 2p, right? So G is a group of order. And similarly, if you start from right from the first power, second power, you will see that there is no power lesser than 2p. 2p is the least number because 2 and p both are primes. And this is the least. Also, you know that order of yx, is equal to order of y into order of x. If mn are relatively prime, so order of if xy is equal to mn, which is equal to order of x into order of y. So from here, by using even the formula for order of two elements, or using this, you can write directly. So that's why this is the least positive integer 2p. This means that, this shows that where 2p is least, where 2p is least, right? So this shows that G is in fact yx, such that yx power 2p is the identity, and you know what is this? This is isomorphic to C2p. So I have established that if p divide r minus 1, then you have the group C2p, and the rest of the case is so easy. The second case is if p divide r plus 1, so this implies r plus 1 is equal to pt dash, where t dash belongs to z. So this implies r is equal to minus 1 plus pt dash. Putting in 1, you will get yx y inverse is equal to x power r x power minus 1 plus pt dash, which is equal to x power minus 1 x power pt dash, which is x power minus 1 x power p power t dash. So this is equal to x power minus 1 into identity, which is equal to x power minus 1. So right, it's a similar fashion as we have discussed in the previous example, a group of order 6, right? Okay. So from here, you see that yx y inverse is equal to x inverse, or yx is equal to x inverse y. Thus the group is, thus G must be equal to x y, such that x power p is equal to y square is equal to e, with yx is equal to x inverse y. And you know, everybody knows that what is this? This is in fact isomorphic to dihedral group of order 2p, that's TP. Some people like to write dp. Okay, so I have shown that these are the two possibilities, right? So whenever a group of order G is of order 2p, then G is isomorphic to either C2p or dp. So these are the two possible groups of order 2p. So look at this a little classification, that if I summarize the idea, so you see that 1, 2, 3 and 4, 5, 6, 7, 9, 10, 11 and then 13, 14, 15. Now I have discussed these groups. You know, this is the identity group, abelian. A group of prime order is abelian. This is abelian. This is abelian. A group of prime square, p square, is also abelian. I have discussed earlier. This is abelian. This is a group of prime order is abelian. So there are only two groups. One is C6 and the other is D3. And this is abelian. And this is abelian. There is a group of order p square. This is 3 square. This is equal to 3 square. This is equal to 2 square. This is abelian. I mean, there does not exist any non-abelian group of order 9. So here the first non-abelian group. So here is the non-abelian group is D3, and here here there is a non-abelian group of D5. This first second non-abelian group. This is abelian. This is abelian prime. Every group of prime order is abelian. This is here as a non-abelian group, that is D7, and this is cyclic, so is abelian. So till that, and now also you see that there is exactly one group of order 2, which is C2, right? Which is C2. There is exactly one subgroup of order, which is C3, and there are two subgroup of order 4. I will explain after the definition of direct product and semi-direct product, that how you can find the other groups. Okay, or I'll elaborate in some other lecture, that there are two possible groups. In fact, there are two possible groups of order 4. One is C4 and the other is C2 cross C2. But till now we have no idea about direct products. So after defining the definition of direct product, I will show you that C2 cross C2 is in fact V4. So okay, so there are two groups. One is C4 and other is V4, right? C4 and V4. C4 and V4, but both are abelian. This is Klein 4. And there's exactly one, which is C5. There are two, one is D3 and other is C6. There is exactly one, C7. There could be two, one is C9, other is C3 cross C3. This will be studied later, inshallah. And there are two, one could be D5 and other is C10. There is exactly one, that is C11. This is C13. There could be another one, that is C14, and this is in fact C15. Okay. Okay, till now, by using the applications of Sylow's theory, we have discussed these groups. And then after studying direct product and semi-direct product and the definition of extension, we will try to find more groups. Okay, thank you very much. Allah Hafiz.